We go. Just first, a quick reminder of where we left things at as far as atomic history goes. We said that Bohr, he was the one that was able to identify where those electrons are located. Up until this point, we had Rutherford who said, yeah, all of those positive particles are contained in that really dense, positively charged nucleus. And instead of having and then Bohr comes along and said instead of having these negatives, these electrons just floating around in that pudding mixture out there, they are contained in these definite orbitals. So that's what Bohr contributed. And you've got these notes in front of you. This kind of just describes what we've already talked about, that Bohr's model of the atom was based on the planetary model. And just like planets, if you have the sun right here in the middle and you've got these planets orbiting the sun, they don't come crashing down towards the sun. And there's a couple reasons for that. Yes, they are attracted towards the sun due to gravity, but you've also got inertia going where they continue in that straight path due to inertia. So eventually what happens is you get that curved path where they're orbiting the sun. Similar thing with electrons and protons, that attraction between the electrons and protons, the positive and negative charges, and they just orbit around that nucleus. So that's pretty much what the first couple paragraphs of your notes kind of describe for you. Then we get to this part. The Bohr model also explains the fact that only certain frequencies of light are emitted by atoms, and the electron can travel only in certain orbits. So we remember these electrons are only in these certain orbits, which means that the electron is quantized. So as opposed to having an infinite, continuous spectrum of different wavelengths or frequencies of light that can be emitted, what we're seeing is that we only get these very discrete frequencies that are emitted. And you can't see this at home, but it would be like if I'm standing on a stair here, well, I can be on this step or I can be down here on this step, but I can't stand in between those steps. So it's the same thing with the electrons. You can be in this orbital or you can be in this orbital, but there is no in between, so it's quantized. It's a definite discrete amount of where it's located. Okay, so when the electron is in its lowest energy state, actually let's stop for a second and write ourselves a note. Find this, my paragraphs are a little bit different, but find a little place over on the left-hand side around this point and write yourself a note that this refers to the hydrogen atom. This refers to the hydrogen atom. So we know the hydrogen atom has one electron. And that one electron, when it's in its lowest energy state, its most stable state, it's said to be existing in the ground state. So you should know that term. The ground state is just its lowest energy level. It is its most stable energy level as well. And that energy level is going to be the orbit that is closest to the nucleus. So this orbit for the hydrogen atom, this orbit is going to be n equals 1, because when we refer to n, we're talking about orbits or energy levels. Same thing. So n equals energy level, and for the ground state, for a hydrogen atom, that n is going to be equal to 1. Then what happens is that atom can gain energy. So it goes, when it gains energy, it goes into a higher energy state, and that's known as an excited state. So if that atom absorbs energy, the electron jumps to a higher energy level because it's pushed, basically. That absorbed energy pushes the electron to an orbit that is further from that nucleus, so that's a greater amount of energy. And those excited states for the electron would be anything 2 and greater. It would be greater than that 1. So as we're seeing from this, as you move away from the nucleus, the energy gets greater and greater. That's what we're seeing there. So greater energy out here. It increases in that direction as you move away from the nucleus. So now what happens? We said that if this electron gets excited, it jumps to a higher energy level. Well, just like us, if we sit there and eat a whole bag of Skittles, we're going to all of a sudden be really excited, have lots of energy, greater energy level, and then you can't last there for very long, and finally you're going to have to fall back down to that ground state. And that's what's happening here. So when the atom returns to the ground state, the electron falls from the higher energy level or the higher orbit back down to the first energy level. And in the process, the difference in that energy is given off as light. So it's the process of falling back down from an excited state to ground state that light energy is given off. And the frequency of that light is going to follow Planck's equation, which we talked about last lesson. So we can see that frequency is part of this equation right here. There's also another way that we can relate to frequency, and that has to do if we know something about the energy levels, where they started and where they ended from the excited and ground states. So that brings us to something known as the Rydberg equation. And just to let you guys know right away, this will always be given to you. You do not have to memorize the formula or the constant. That will always be given to you. And so from this, we see that we can calculate the frequency of light just using a constant and information about your final energy level and your initial energy level. So we'll do that in a few slides. First of all, though, let's just say a couple other things about these electrons. So white light, when it passes through a prism or through raindrops after a little sun shower, then oftentimes you see this continuous spectrum of color. So you see this rainbow. But if you were to take this gas and heat it up, and this gas then goes through a prism, we can get something known as an emission spectrum, which is seen right here. And an emission spectrum is just showing those very distinct or very discrete bands of color that relate to what's being emitted due to how those electrons fall from those higher energy levels to the lower energy levels and the frequencies that are related to those. So this little example that I have down here, by no means should you memorize something like this, and there's no way that you would know that it is a blue line that results. But right here, we have this blue line, so this might be an example of how that blue line is emitted. That you have an electron that jumps to a higher energy level, maybe the 5th energy level, and then it falls back down to maybe the 2nd energy level. And falling down to the 2nd energy level, what happens is that we have a color of blue that is given off in this example. So based upon where it fell from and where it falls to, you get different frequencies that are emitted. And then this is just showing a slide that shows where these bands of color, it's kind of hard to see them on here, that you've got these different bands of color. Again, this is the emission spectrum, and we see how this is created. This is the same process for how we can discover what elements exist on stars through something like the emission spectrum. Okay, so now back to your notes. We see we've got this figure here, and it shows energy levels of the Bohr model, and it's explaining the line emission spectrum. Again, this is for the hydrogen atom. That was kind of a downfall of Bohr's model, is that it really explains things for the hydrogen atom. Not so much some other things, but that's okay. We'll take care of that stuff later. And as you read through these notes, let me just kind of skim through a couple things first, and then I'll come back to this. We see that when it falls, when an electron in an excited state falls to the 1st energy level, we see that UV light is given off. If it falls to the 2nd energy level, we see visible lights given off, and if it drops to the 3rd energy level, we see that infrared light is emitted. So all of that is summed up for us right here in this little figure. So let's make ourselves a note maybe, that if our final energy level is equal to 1, then we see that UV light is emitted. If our final energy level is 2, we see visible light is emitted. Or if our final energy level is 3, then that's going to mean that infrared light is emitted. And yes, you get to know that. That's something you should commit to your memory. Okay? So that's what we see as far as what is emitted when these electrons in this hydrogen atom drops to these energy levels. This, when you guys start doing your homework, you're going to see, I think like number 2, for example, it says something about sketching a Rydberg diagram. What I would expect for that is these parallel, straight parallel lines, and then showing what's happening with going from what energy level to which one. So it's going to be something like what you see right here. Then it also says sketch a Bohr diagram, which is very similar. It's just concentric circles instead of these parallel lines is the only difference, but those will be very similar. Okay, so we've been through this, which now takes us to the math part. Here we have our equation, a little reminder up at the top, and our question is, what is the frequency of light resulting from an electron falling from the 7th to the 1st energy level of a hydrogen atom? Again, note that we're talking about a hydrogen atom. Okay? So we want to figure out our frequency. We're going to say frequency is equal to Rydberg's constant, so 3.288 times 10 to the 15th. That's in cycles per second, which is just seconds to the -1. And, sorry, I don't know why I put an equals there. So we're going to take that and we're going to multiply that times 1 over our final energy level squared. So that minus 1 over our initial energy level squared. And I should have let you guys kind of guess that, but hopefully you can see that this is our final. It fell from the 7th, which is our initial, to the 1st. So here we're going to have 7th squared. When you guys start writing these down, I just wanted to show this like that one time, but chances are you're just going to do this. One minus, or actually maybe you'd say 1 over 1 minus 1 over 49. So feel free to just jump to that step right away. So I'm going to pause as everybody calculates. Okay, awesome. They did it, and they also knew that they were going to keep it as 4 sig figs by doing that. So that's all there is to this. We go on to the second one. Here it says, what is the wavelength? Getting a little trickier because I don't see wavelength in this formula. We want to figure out the wavelength. Ooh, I skipped something. Going back to this one, I didn't answer this part. It says, what type of light is this? How do you know it's UV? The 1st energy level, yay. So we look at this, and this tells us if it drops down to the 1st energy level, then UV light is being emitted. Yes? Okay, so I also had a question as how would you sketch something like this, because I know that you guys will have to do this on homework. So what we're doing is we are going from the 7th to the 1st. It is just this easy. If I can count 1, hold on, 7, 6, 5, 4, 3, 2, 1, I can count. So the way you would sketch this, like that. There you go. There's your sketching. I did that for Rydberg, so you could also do that for Bohr, but instead of making it these parallel lines, you get to do concentric circles. That's all there is. Okay, so now moving on to number 2. We said that we're trying to figure out our wavelength, and wavelength is not part of that equation. And we know that the electron falls from the 3rd to the 2nd energy level of a hydrogen atom. We also want to know the type of light. So based on this information, what are we going to solve for first? Frequency. Good. So we're going to solve for frequency using this equation. So let's just go ahead and do that first. I'm going to say my frequency is equal to Rydberg's constant of 3.288 times 10 to the 15th. Yeah, I'm going to throw some units in there, but remember there aren't any other units, so that means that's going to be the units for my frequency here. And we are going to multiply that times, what is our final? Second. So I'm going to say 1 over 2 squared, which is 4, minus 1 over 3 squared, which is 9. And people are going to calculate. All right, so we've got our frequency figured out. But the question is, what is the wavelength? So now, what formula do you want to use? What do you think? Awesome, awesome. Okay, so we're looking at our formula that we used on Friday, a couple lectures ago, which was our speed of light equals our wavelength times our frequency. And when you solve that, For wavelength, you end up saying it's your speed of light divided by your frequency. So really what I'm doing, I guess you could say we're using algebra. I know we've been stressing dimensional analysis. I'm using algebra, but I'm showing my units to keep myself honest and to make sure I'm not making any mistakes. So I'm using some dimensional analysis in there as well. And I am going to say that it's 3.00 times 10 to the 8th. That's in meters per second. And I am going to divide that by my frequency that I just calculated, 4.567 times 10 to the 14th, 1 over seconds. So when you divide by a fraction, you multiply by the reciprocal of that. So there's my seconds up there, which looks good. I would expect my answer in meters for wavelength. And that's all there is to it. It doesn't ask, it just says wavelength. It doesn't specify nanometers, so just keep it simple and keep it as meters. And our answer, let's see if everybody, 6.569 times 10 to the negative 7. Looks good. And then that's going to be in meters. Fabulous. Okay, second part of this. What type of light is it? Visible. You guys are so smart. Okay, so we know because it drops to that second energy level, we know it has to be visible light. Okay, so even though you might have thought last lesson was a little complicated, you just did it. You just applied that. And the math wasn't tough on that. The units made sense. So you guys did it. Okay, last one that involves calculations. Here it says, when an electron in a hydrogen atom falls from a certain energy level, it emits light in the visible range. What does that tell us? 2 for our final. And the question is, what energy level did the electron fall from? So in other words, what is our initial energy level if the wavelength equals 410.2 nanometers? Starting with wavelength, what do you want to solve for? Frequency. And we're going to do that using this formula. So we're going to say our frequency equals our speed of light divided by our wavelength. So there's our speed of light divided by our wavelength is 410.2 nanometers. Uh-oh, nothing cancels. So let's make it cancel. Make your meters go away. Make your nanometers go away. How do you do that? Which one's bigger? Meters. One of these big things, 1 times 10 to the 9th of these little things. Bye-bye. They're gone. So you have your answer in 1 over seconds, which is exactly what you would expect for frequency. And we get, let's see here. Actually, on my answer sheet, I've got this as 2.998 instead of the 3.00. So mine, I think I corrected this, but 7.314. Okay, good. 314 times 10 to the 14th seconds to the negative 1. There we go. So we've got frequency, but we're doing something a little bit more complicated. This is when we start getting to some really fun math. So now what we want to do is we want to plug this into Rydberg's equation and solve for the actual energy levels. So I'm going to take that frequency, 7.314 times 10 to the 14th, and that's in seconds to the negative 1. And I am going to set that up equal to Rydberg's constant. Times 1 over our final energy level squared. And what is that number going to be down here? 4. Minus 1 over our initial energy level squared. If you want, you can just think about that being an x right there, down there. So now this is going to take a little bit more time as everybody solves for the missing variable. Put your math skills to work. It's fun. Okay, so some people in this room have breezed through this. Other people are still struggling, and the looks in their eyes are not so fun looking there. I'm going to go through the math. This is what you would do, step by step. I would take and divide by the 3.288 times 10 to the 15th. I would divide by that on each side. And then once you do that, you get, what do you get? You get 0.224, no, 22, I don't know, somewhere around there. You get that number when you divide each side by Rydberg's constant. And then you're going to say that that equals 0.25. All I did was change that to a decimal, minus 1 over ni squared. Okay, so that, yeah, you wouldn't want to distribute in this, just divide by each. Okay, so now we've got it to this point. I'm going to, since this is negative, I'm going to get this on the other side. That personally makes me happy to do that. So it ends up being positive 1 over ni squared equals the 0.25 minus 0.2224, and you get something, my numbers might be rounded slightly differently because I kind of did this really quickly with my new numbers. Remember, I had used a different value up here. So you get it to this. Everybody should be able to get 1 over ni squared equals 0.02755. Then, a couple ways you can do this. A really easy thing to do is to say, well, I know that this is the reciprocal of that. So just hit the x to the negative 1 button on your calculator. Or you could say 1 over second function answer, if you think about how to use that on your calculator, if you know what I'm talking about. Or 1 over 0.02755. If you're not sure why you're doing that, think about cross multiplying. So you know what you're doing there. Then you get ni squared equals, I think somewhere around there. When I used my 2.998 times 10 to the 8th, I was a little bit closer than this. But now knowing, being able to look at that and saying, yes, when I get the square root of that and get a whole number, my initial energy level equals 6. So that is it on that one. Okay, so now that leaves us just with a couple more problems. Next one, here it says, how many emission lines can result from the falling of an electron from the 4th energy level? These are just as simple as they seem. 4, 3, 2, and 1. So our possibilities can fall all the way down, can fall to the 2nd energy level, can fall to the 3rd energy level. So how many? 3. That's it. The question is, would you have to show work for that? If I asked that in a quiz form, I think I would like to see the diagram, but chances are I would say also sketch your work or something like that. Okay, and then last one that we have. Here it says, what is the difference between an absorption spectrum and an emission spectrum? What we have seen so far in this slide show is that we have seen the emission spectrum. And the emission spectrum is going to be when you have the wavelength, those colors are absorbed, emitted. Sorry, I'm looking at emission spectrum. It's backwards than what you guys have on your paper. So in the emission spectrum, the wavelength of colors are emitted, whereas in an absorption spectrum, you have the wavelengths of colors are absorbed. So just like it sounds. Again, this is what you guys have seen with what we've done so far. The emission spectrum is how we determine what the composition of stars and such is. And you can see those definite colors being emitted. Here they're absorbed. That's all we've got, just to kind of keep things going here with the history. We're not going to talk about this unit, but next unit we're going to talk about how this whole idea of the atom has been amended even more, and we're going to look at something known as the quantum mechanical model. It has to do with Schrodinger. You've probably heard his name before. So that's all we've got. Nice job.